Hello again. This video will be about the midterm. So this is the midterm you guys took. I just copied it off of Bayard. I didn't have to save to my computer because I didn't have the final version saved. Anyways, just so you guys know how to solve these, I'm going to go through them. Now, that said, I'm going to run through this like I'm taking a test, except I'm going to narrate out basically my thought process so that you can understand how I think about this problem and how I get to the solution. And I'm going to be basically doing this like I'm doing the test. You guys can even time me, well, you can see by the video, how long I take to do this. So you can get an idea of how long it takes to do this test, if you've already gone through this. Now, it will take me a little slower than I usually would because I'm going to take my time to explain things and run through it. But generally, the amount of time I take to go through this entire thing should be about the same amount of time you'll need to, just because I can do it faster, but I'm doing it slow so I can explain it to you, so that'll make up for my speed. I'll also say that me taking this will actually be about the same. Me going through this will actually be about the same as you taking the test. Yes, I think I wrote one or two functions in this test, but otherwise I haven't actually looked. I've seen the other problems, but I haven't actually tried solving them yet. So I haven't even thought about how to solve them. So basically, I'm going to be doing this about the same as you guys did on the test. So, with that said, let's get started. Let's make sure I'm actually recording. Yeah, okay. Sorry. Okay, anyways, okay, so this is the first problem. Given a list of sublists, so list of int, cool. A function which returns a single list. Okay, so we need a single list containing minimum of every sublist. Use folder when finding the minimum. Ignore empty sublists. Okay, so we have so here's how I'm thinking about this. Okay, so we need to use folder when finding the minimum, but when we have an empty list, we should return an empty list, or we should what? Ignore them? Yeah, we should probably ignore them. So, okay, so I'm going to, so we need to ignore the empty list, but we need to use folder. This presents a problem because let's say, so here's what I'm thinking is, okay, let's say I have a function like this, okay? When you're using folder, if we do something like folder, something like this, and then x, or something like, I don't know, given x and y, we take the min of x and y, something like that. That's cool. Like this would work, I'm thinking, because we give two elements, we just return the min of the two. I'm pretty sure min is a predefined function, but I'm just gonna check. I'm not using the clean browser, but if you're using the clean browser, you could just search in clean. So let me just make sure min is a function. Yeah, min totally is. Okay, so yeah, this would work. We can grab the min of two items. The problem is that we have to always take the first element as our first element here, because otherwise we don't know. We can't set like -9 billion. That's not the good way to do it. The only problem is that if we always have to extract first element, it won't work on empty list. So I'm going to try to do it as a separate function. So I'm just going to call this min list folder. Min list folder. So it takes a list of integers and it returns a single int in list. The reason why I'm going to do this is because if it's an empty list, I should actually leave it out completely. But if it's empty list, I can't return nothing. So I'm just going to return everything inside a list, so that with empty list, if I return an empty list, it'll just concatenate an empty list and disappear. So I'm just going to say this. If we have an empty list, we give back an empty list. So if we have empty list, it will return that, and when it concatenates here, it'll be cool. Cool. List folder. So let's say we have the first element and the rest of the elements. Okay. This pattern match should be familiar to you guys. So I'm gonna say folder given x and y equals min of x and y, and the first element has to be the first element, and we're gonna have to operate on the rest. Okay. So before we, as always, before you guys whenever you make any subfunctions, always test it. So min list of 1, -1, something like this. So let's test this out. CD, where am I? This is test. Oh. CD CLM midterm and /a .out. Okay, so let's see. Whoops. Let's see. Midterm the 2019-4- this file name is not about file name. Okay, hold on. Sorry for the technical difficulties. Let me fix this. Clean, why are you so picky? Okay. Okay. So CL midterm and /out. There we go. Okay. Lifted argument R4 cannot be offered with blah type. Okay, cool. So we have function, first element, rest is the rest of int folder. So given an x and a y, take the minimum of x and y. We have first and the rest, and I don't think it's that, but let me just check. Yeah, okay, so oh, right, right. I forgot to throw it in the middle of the list. Yeah, that's right. Okay, so yeah, this works. Let me try it with -1. So the last one at the end. Yeah, okay, it works. All right, so my little auxiliary function works. Cool. And then now that I have one that just operates on a specific list, get min on a list. So get min on a list is equal to well, given each sublist. Let's say big list. So given each sublist from the big list, we're going to do min list folder. God damn it. Min list folder on the sublist, and then we need to flatten this. So flatten. So now we can track this. This should reject all the empty lists and return that. Yep, that works. Let's check it with one with the empty list. Yep. Okay. Yep. Sounds good. Looks good. Okay, we're good here. All right, let's keep moving on. All right, number 2. Given a list of tuples, return a single tuple, which is a sum of all tuple x and y with blah blah blah. Oh yeah, the parity one. Okay. Yeah, so x and y either have to be odd, even, and then you have, so if you have tuples that are, so just to clear out, if you have 1 1, if you have 1 1, and then you have 2 2, and then you have a 1 3, you add this. What you have to do is you have to do 1, so the 1 from here plus the 2 is minus the 1, so 1 plus 2 minus 1, and then you have to do 1 plus 2 minus 3, something like that. Okay. So let's run through this. Okay, cool. So given a list of tuples, we have to do that. What, we just have to sum them all up? Okay, so tuple sum. So we have a list. Okay, so So our element from the list, what do we have to do? Well, let's just say if, okay, well, since it's a tuple, I'm just going to pattern match it instead. So A and B, okay, so we now have A and B is even A is the same as is even B. So we have the same parity. You don't need, a lot of people separate the case where it's like odd, even. You don't have to do that. They don't, people did like is even A equals, if is even A and is even B, or it is odd A. No, you don't need to. Because if it's odd, this will return false, this will return false, and they will be true. So if they're both odd, it will be false, false. This is both true, true, true. So this is all you actually need to do. So if they're both true, we will put A and B here. So yeah, we can do that. So we put A and B here. So I'm just, how to say, we're separating these lists here. So we're going to separate these lists. What's the best way to do that? I mean, I need to add them up somehow and keep adding them up. But we need to add up tuples and return a single tuple. So what I'm actually going to do, so because right now I'm trying to run for time, I'm going to make an instance on tuple. I'm going to make an instance of addition for tuples of two types. So given int is where plus on a b c d is should give us a plus b comma c a plus c comma b plus d. Let's test this out. Start equals 2 plus 3 4. So yep, that works. Okay, so there you could make a separate function to add them or whatever. I'm just going to do it with an instance. And in fact, I want to use the sum, so I'm going to make an. I already know off the top of my head that sum requires a 0 instance, but if you didn't know that, you can also equals 0 0 0 0. The reason why I know that is because I've used sum plenty of times before. If you don't know that, you can look up sum. Sum requires a 0 and an addition. Okay, so let's just test it just to make sure. So I can do sum of 1 2 3 4, and this should work if I did it correctly. Yep, it works. Okay, so now I have both instances, so now I can use this. So what I did was this list comprehension will filter out ones of the same parity. So I'll do, and you know, I'm going to do where lines just to make it easier. So I'm going to be same equals sum. So same will be the sum of all of these guys, and different will be the sum of all the guys who are not like this. So it's going to be exactly the same. Actually, I'm going to copy this interior, but this is where they're not of the same parity, so it's going to be like that. And then I'm going to do same minus diff. So this is sum of all of the guys who have the same parity, sum of all the guys with different parities, and then we subtract the second from the first, and this should work. So let's check it, unless I made a mistake. And of course I made a mistake, because it didn't define subtraction. Okay, that's fine. I'm just gonna subtract. We're subtract. So we're just subtracting here. I'm just making an instance of subtraction. This is why you use instances. It makes your life a little easier. There. Okay. It makes your life easier because you could just be like, okay, well, we just want to subtract. We just use instances, and we can use all of our basic operations. Okay, let's see. 3 and 2. Yep, that works. Okay. And let's go here and check this one too. 0 and 3. Okay, good. Good. So that one's done. All right, let's move on to 3. Let's see how long I've gone for so far. I've gone on for about 14 minutes. Cool. Okay, I'm going at okay pace. 3. Write a function that takes a list of tuples, each tuple containing a pred function int. What's this one? Oh, conditional one. This is the one I wrote. List of tuples, each tuple list of integers. Return the sum of sublists where all predicates return true for that. So, okay, so we sum up the sublists, but only if the sublist, let's see, does not return true. Okay, yeah. So if the sublist doesn't return true for all of them, we leave it out. If it does, then we sum it up and add it to the list. Yeah. Okay. So this I believe because I wrote it. You can do it with a single list comprehension because I'm lazy like that. So given the thing about this is that we have a list of tuples. So this isn't quite. So what we have to keep in mind is that we have a list, but each list is a tuple. So each list element is something of like a condition and a list of integers that we need to process. So our list is made of these. So we have to keep that in mind. But it doesn't matter. We're just gonna say we have a list. We want a list back out. I'm gonna do list comprehension. I'm gonna call this big list. So we have big list, okay, and from the big list we're gonna get sublists out. So each sublist, okay. So given a sublist. Oh wait. It doesn't give a sublist out. My bad. What it gives is a tuple out where we have a condition and a sublist. Yes, I have to keep that in mind. Okay, so we need to filter them. So the ones that don't return true for on this condition on the entire sublist, we have to not deal with it. So we're going to say map con to the sublist. You can also write this with a list comprehension, but just to keep things a little simpler for you guys, I'm not going to list comp inside list comp, but you can easily do it. And. Okay, so why am I doing that? Map con on sublist, so we map this condition to each element of the sublist. And then we do a big and on top of it to see if they're all true. Okay, if it's true, then we're going to, what do we have to do? We have to sum up the elements of the sublist. So we do sum on sublist. Okay, cool. This should work. Unless I made a mistake, which I probably did. No, I didn't. Awesome. Okay, cool. Yeah, 209. All right, awesome. Let's see. Nope, go here. Let's go. Come on. Okay. And let's check this one. Cool. Okay, cool. That handles all of that. As you can tell, whenever I write and you'll see this on the end term also, I'll write problems that may sound complicated or whatever, but they're actually horribly simple. I'm too lazy to write anything horribly complicated. Write a function which takes a list of numbers, contain a palindrome. Oh, so we're filtering. Okay, so we're filtering out palindromes. Okay, so we need some function that tests for palindrome. Is pal given an int gives us a bool. Cool. So is pal int gives us a bool, but we need to turn. So first, before we do that, let's just convert our integers into lists. So int list takes an int and gives us a list of int. So how do we do this? We're going to int list x is equal to well, let's keep it in order. So we're going to do x rem 10. So this will grab the last digit out of it, and we need to concatenate it to a list of the rest of it. So we've done this in homework, so if you don't quite know it, I would say go over the homework. Int list of x divided by 10. Of course, we need this in parentheses, and we need a condition because there's a recursion, so we need to stop it. So if x less than 10, we just give x back up. There you go. Okay, so let's test this out before we run it. Int list Okay, let's see. Does it work? Yes, cool. Okay, cool. So if we need to check if it's a palindrome, we can is pal of x is equal to where list is equal to int list x. So we turn it into a list, and then we check if list equals reverse list. So if it's equal to its own reverse, then it should be a palindrome. Let's test it. Equals is pal 1 2 3 4. That should return false. Yes, of course that's false. And let's test another start equals is pal 1 2 3 2 1. Should return true. Yes, of course it returns true. Cool. All right, cool. Now we can do this palindrome one. So basically, we just have to filter it for palindrome. So given a list, we equals filter is pal on the list. That should basically cover it. So let's check that. Doink. Does it work? Yes, it does. Cool. This one. Yes, it does. Yep, works. Yep, works. Okay. So as you can see, it's actually not that hard. It's mostly what we did homework. I'm trying to run through this quick. Leap year, leap year. Oh yeah, here. So what is it? Generates a list of the first n leap year starting from layer x. If okay, so we have to generate a list of leap years based on some parameters. So I'm gonna need something to tell me if something is a leap year first. So I'm just gonna make a function for that. Because we need to know if something's a leap year. So is leap year n int. So we've given an integer which should be our year. We're gonna return a boolean, true or false. Is leap year x. So if x is a leap year, well, let's just straight up copy this. So if a year is divisible by 4, then it's if it's not divisible for x rem 4 is not equal to 0. So if it's not divisible by 4, then it's false. If it's not divisible by 100. Okay, so if it's x rem 100 is if it's not divisible by 100, then it's true. Okay, x is not divisible by 400. So if it's not divisible by 400, then it's false. Otherwise, it's a leap year. Otherwise, true. Okay, cool. We could test this. Just to start equals is leap year 3. Let's do 1993. This should not be a leap year. Yes, of course. Let's try 2000. This should be true. Yes, of course. And let's try 2100. Should be false. False, of course. Cool. Okay, that's most of the cases. Cool. We have to do leap year. So leap year is what? First n leap year starting from year x. So let's see. So okay, so the first one's a year. Leap years, year and n. Okay, so given a leap year, we have to generate leap years based on that, excluding it. Okay, cool. So okay, I'm gonna do list command. We're building a list. So we're gonna say n years. Okay, so we need so I'm gonna call this x. So we're gonna say year. Well, actually not year. We have to exclude the year. So year plus 1, and we're gonna do infinite list. Later we can take as many as we need. So years starting from the one after the actual year itself. If it's a leap year. So if that year is a leap year, we will keep it, but we only want to take n of them. So this should work. Let's check. Unless I made a mistake. I probably did. Nope, I didn't. Cool. Let's see. Well, that's an issue. I didn't check for negatively. Yes. Okay. Year sine of year times sine of n less than 0 equals for those of you wondering what sine is, it's a very convenient function. Sine is something that's already exists. It gives you a -1 if it's a negative value. So if either of them are negative values, we should give 0. Actually, this shouldn't work because if they're both negative. Okay, so I was going to try and do something that's fancy, but year less than 0 or n less than 0. We'll just do it that way. So I was going to do it fancy, but I realized that won't work. Yeah, okay, so that handles that case. Because if they're both negative, it should also fail, but yeah, okay, that works. Cool. Okay, moving on. This leap year thing, as you can see, I directly translate something that would be a very imperative statement to basically functional. Because it's just an if else, if else, if else. Now you can make this better. Some people did in one line. Right now, I don't care. I don't have time. I'm trying to do this as fast as possible. Well, what's this one? Write a function that takes a number and determine whether or not it's a perfect number. What is a perfect number? Natural number that equals the sum of all its proper divisor. Proper divisor is every divisor of a number excluding the number itself. Okay, so 6. So 6 is divisor 1, 2, 3, and 6, but we exclude 6. So we need something to get proper divisors of a number first. So int gives us a list of int. Int. So we need to generate list of proper divisors first. Oh my god. Okay, so given an x, what do we have to do? And we need to go from 1 all the way to x minus 1. And if, x rem n is equal to 0, so if it does divide that, we'll keep n. And we can test this out. Start equals prop div, let's say 10, which has a bunch of divisors. 1, 2, and 5. Cool. Okay, cool. So, okay, that works. It's perfect. So, no, that should be fairly okay now. So, if we have an x, it's x equals sum of prop div x. That should work. Well, let's check. What did I mess up? 151. I forgot the space one. True. Okay, cool. Who did this? Whoever wrote the problem put a little space in front of everything. True. Cool. False. Cool. This will be a problem. We're gonna run into problems there. That's good, but this will be a problem. 0 might cause a problem. Maybe, maybe not. False. That's a problem. We need to code in a 0 case, and I think we had to code in a negative case. Yeah, okay, cool. But that's easy. We could just guard it. Guard. So x less than equal to 0 equals false. Yeah. And I really don't even need to test that because I know it'll work. Okay, given 2 integers, return a list of all common divisors of 2 integers. Let me check how I'm doing time. Oh, I'm only half an hour in. Cool, and I'm on number 7. Cool. Given 2 integers, return a list of all common divisors of the 2 integers. Integer. Okay, list of all common divisors. So so here's what I'm thinking. Here's my thought process about this. Is that and this will come from you guys studying the pre-built-in functions. We can generate a list of divisors between each number, and then we need to get the common one. So we need to get some sort of intersection between the two. I happen to know in standard list. So if you look up standard list, where is it? Come on. Doing somewhere here we have something that checks for common elements between them. Okay, is any member check that the intersection between. Oh, this only returns a boolean. Isn't there one that returns the commonality? Oh, is there not? Oh, there's gotta be one. Oh, don't betray me now. Come on, Clean. I know you have one like that, right? Oh. Oh, I thought there was one. No, I could have sworn there was one, but duplicate remove members. First occurrences of the elements of second list from the first list. Oh my god. Oh man. I thought there was one. Okay, well, we'll just have to write our own. Okay, so we'll write our own intersection. Intersect, which will take a list of integers, another list of integers, and give us a list of integers back. So intersect x and y. So these are two lists. Given that, how to say? What we'll say was that elements from x, okay, given that n is member n and y. So if n is inside of y, we'll keep n. And yeah, because we just want their intersection. And we also want, and we'll concatenate that with the intersection of the members with, yeah, so we'll put them all together. So, and, okay. So, and from y, given that is member n of x. So if n is a member of x, we'll keep it. This from y, blah, blah, blah. We can test this, start equals intersect, okay. 1 to 10, my bad, and 5 to 20. So this would give us something between 5 and 10. Come on, let's go. Yes, gives us 5 and 10 doubled, but that's fine. It's fine. Okay, so now we need divisors. So we need somebody that generates divisors. Yeah, we'll make something that generates divisors. So I'm going to div of int gives us a list of int. Are we including one? Let's see. Are we including one? We are not including one, but we are including these numbers themselves. Okay. So for this one, we're going to say, given an x, we're going to generate a list of divisors. So n from 2 to x. Yes, because we include x. Given that x rem n is equal to 0, so given that it actually divides that, we'll keep n. Cool. So now we have to divisors of x and y. We're going to say div x, div y. So these are the two divisor lists of, so this is the divisor list of this. This divisor list of this. I'm going to intersect them because I already wrote that function. And because there are a bunch of duplicates there, I'm going to remove dupe. Okay, so this should work. Let's go. By the way, these solutions are just my solutions off the top of my head. They're not the most optimized, and there can be better. But I'm doing this as if you're doing a test where you just want to get it to work first, and then if you have time, you can optimize. But this is pretty nice anyways. This is 3 lines. It's not so bad. You can do it in 1 line probably, but right now I'm just trying to go for speed to show you guys. Right, what's this? Cubes 2. Oh, should I test the other ones? I should test the other ones. I should test the other ones. Empty list? Okay, cool. And this thing, let's see. Cool. Okay, let's go here. Alright, so 8. Given a list of integers, find all cube numbers, right? Find all the cube numbers, write n to the first, and write n to the first list. Where I will get 2, okay. Oh, so anything that's a perfect cube, we write their cube root, and when that's a perfect square, we write their square root. Cool. Okay. I'm just gonna do it the straightforward way that I've seen someone do, but so we need to find a cube root. So cube root, which would take an int and give us a boolean. So it'll check if it's a cube root. So cube root x is equal to how do we say? Let's say well, okay, let's do this. N. I'm gonna generate all elements from 1 to. I don't even need to go all the way to x. I could do. Well, we can just go to x over 2 because it's clear. And let's just do x. Doesn't matter. Not efficient, but it's fine. N times n is equal to x. So if there's a number between 1 and x that cubes to give x, we keep it. If this is not empty, so if there is one, then this thing should be a perfect cube. We can test this. Start is equal to cube root. This function can be wrote better because I don't need to go all the way to up to x, but whatever. For now, let's check this. Start cube root of 9. Of course, it's false. 9 is not a cube root. 8 is. Yes. Okay. There we go. Cool. And we need a square root one, so we can do a square root. Square root, which takes an int and checks if it's a perfect square. Also, square root of x is equal to. I'm actually gonna copy this one, but I'm gonna change it. So instead of n times n times n, we just have n times n. And I don't even need to test if this works. I know it'll work because the first one works. Cubes. So cubes to. That's a weird name. List is equal to. What do we have to do? Oh yeah, the cubes. Okay, yeah. So filter cube root on list. So this will give us a list, but we need to throw this entire thing into a tuple. Okay, we'll just open up the tuple. Okay, so comma. So that's one of them, and then the other one is filter square root on list, and that should work. Let's see. Boink. Yep. Did I keep order? Oh, we're oh, we need right. I forgot. We need the actual cube root. Okay, that's fine. We don't have a cube root function though. We do have a square root function, but we don't have a cube root function, and we definitely don't have a square root or cube root function for integers. So that's a little bit of a problem. So this will fail. Okay, so we actually need to cube root test. Let's call this test, so that we know that there's a test, and then we'll write an actual function that actually does the. Okay, so okay, well, so cube root, an actual function that actually cube roots something. So cube root x, given that cube root test x, we'll assume it's a perfect cube. I will say I'm going to take this. So I'm going to take this exact same thing. There should only be one value that works, and I'll take the head of it. Let's check. This should really work. Uh-oh. Oh, right. Because go away. Okay, go away. Let's check this. Yeah, okay, 2. Wow, that is hyper inefficient if it took that long. Okay. Now my computer's chugging a bit. Okay, cool. So now we need square root. Okay, oh my god, that int goes another int, and we need to do the same thing. Square root of x equals to, take this, and just take the head of it. Okay, so that should work. So we need to change this function Notably, we can't just filter it, we need to actually process it. So list x from list, given that cube root test on x, so given that it is a cube root, we will store the cube roots, and this one we also have to change to something like this. So x from list, given that it's a square root, we will square root it. Oh my god, square root of x. Okay, so this should fix our problem that we had before. Let's see. 4128. Ooh, what the heck happened here? 6. Wait, what? Oh, this is not square root. This is powers of 2. Oh, I'm so stupid. Oh my god. Okay, well, I would have square root test anyways. Okay, power of 2 test int bool. So as you can see, if I was in a test, I would have just wasted a bunch of time. Equals. Well, we're just gonna do the same thing. No, we're not gonna do the same thing. Okay, so what we're going to do is we're going to generate powers of 2. So the problem is that we don't know how high we need to go. And I'm not going to hard code a solution there. So what I'm going to do is I'm going to say, given some n, a, I'm going to do 1, which is infinite list. So we're just making an infinite list of 0. We're going to make an infinite list of powers of 2. Power of a. Okay, and we're going to take yo. We're going to take yo. So this one is a big list of powers of 2. We're going to take yo. It is so y is less than x. Sorry, x. So x should be on this side. Take yo. No, actually, this should be flipped. So take out that, and then so this is some. Alright, just to make this readable, I'm going to do it in a where clause. Where pow2 equals boink. List equals boink of pow2. Okay, so now we have our list, and now we have to check if x is a member of this list. Is member x list. Okay. So this should check if x is inside of a list of powers of 2, meaning if it is a power of 2. Or less than equal to, my bad. Because if x is in there, it should be there. Okay. Let's see what we have to do. Now we have to get the actual power itself. Okay, so okay, so okay, so we're gonna have to change this. So this is power of 2 test on x, but given that, now we have to do it differently. Now this is a little bit of math, but I'm gonna say how do you get the power of something? ln. Okay, so we don't have base 2, but we can use base ln, so we can do ln of x divided by ln of 2. So this is how you take the power of 2, and then we have to 2 in this. That should hopefully work. Yes, 0.0, and x has to be a real 2 real x. There we go. 126 Okay, this took a little longer because I misread the question. Yep, that works. And I think this should work too. Let's check. Yep, that works. Cool. Okay. Ooh, that wasted a bunch of time. But I'm still going time. I'm at 44. Okay, cool. 9. Write a function that will take a list of integers, return a list of tuples where b is every prime index of the given list, and a is the value of the list at that tuple. Ignore 1 as a prime. Okay. So I know we had a is prime somewhere here. Is prime? Is prime? Is there an is prime? Did we write it in is prime? No, we wrote it in is perfect. Okay, is prime. Okay, so we need to write it prime. Ignore 1 as a prime. Okay, but are we taking... okay, so we need to generate list of primes. Okay, well we'll do this. We'll do an is prime of x. Is prime is an integer which gives up a boolean. Is prime of 1 of x. X equals to 1, less than equal to 1 equals false, so we'll just ignore 1 and 0. Otherwise, we'll say, what is it, x, no, we'll do a list from, what is it, 2 to x minus 1, okay, and we'll feed it into n, and we'll say we'll keep it if x rem n is equal to 0. If x rem n is equal to 0, we'll keep n, and we'll do is nt. So if there are none, whatever. There's a different way to write is prime. This is just the one off the top of my head right now. We need a prime list. So prime, oh my god, prime list is a list of integers, and prime list is equal to x. One infinite list is prime x. Okay, so this is just an infinite list of primes that I'll get to work with here. Only prime position. So cool. So given a list, only prime position. So we get a list of. We have a list of integers we have to process. We have to take it. Okay, so first we need the prime number positions. So where len is equal to length of our list. Okay, indices is equal to take take while less than or equal to I think it's greater than equal to, yeah, len. So no, less than equal, yeah. So len has to be greater than or equal to, and we're going to take it from prime list. So we're taking elements of prime list up till the number. So this will only take 1 and 3, and this should do that. Okay, so we have a list of indexes. So we have the length of the list. So this will be 19 elements. And then we only take the primes up to 19. So, yeah. And then what do we have to do? Equals. So with this list, we have to get elements out of the list. No, we don't have to get elements out of the list. No, we don't. We have to get these indexes. So I from indexes. So because we already have these prime indexes, so we have to take each of them and extract the thing from we know we need a tuple, so we need in the first element of the tuple we need to extract that element. So 3 is going to get 8, but we need to extract, actually, because it's 0, 1, 2, so we have to extract I minus 1, and then we need I itself. So this should work. I probably made a mistake somewhere, but let's check. 5283, that's cool. How about this one? Only prime position on that one? Oh, yay, it works. Cool. Okay, let's see. 2, 2, 3, 3, 5, 5, blah, blah. Okay, yeah, that works. Cool. And what about this one? Oh, yeah, this was the... Okay, cool, it works. Okay, there we go. That's that. Cool. Fibonacci, Fibonacci. Okay, cool. Yeah, let's do this one. Big T of x is equal to. Well, first we need to code in some of the hard code solutions. T of 0 is equal to 0, T of 1 is equal to 0, T of 2 is equal to 1, yes. T of x is equal to T ox, we're going to need a T ox, which will have, so we need to keep track of we need to keep track of 1, 2, and 3. The 3 previous numbers, and then we need a current number. Yes, so instead of, so in Fibonacci, if you recall, it was you keep track of the 2 previous numbers and you add the first 2. But here we're going to keep track of the first 3. So we need at least 3 numbers. So we're going to say 0, 0, 1. Okay. So if let's guard this. X is greater than 2. Because if it's less than 2, we shouldn't even return anything. But we also have to cut out all the negative numbers, just in case. Otherwise, we'll just return a 0. Anyways, now we need to do a tox. Tox, which takes an int, and gives us back a single int back out. So what are we doing here? Tox. So the first one, so we have a, oh my god. So I'm gonna call it T. Okay, so how is this? Tn minus 1, n minus 2, n minus 3. So T, well, I'll just call this A, B. A, B, B, and C is equal to yes, right? But we actually need a counter also. Oh my god. Yeah, okay. So, and then there's another int. I'll admit this one is one of the more complicated ones. Okay, so int, this one will keep track of where we are. Okay, so if we are at T0, T1, actually this should be 0. Zero, 1, 1, something where it's like if n is if n is greater than, this is going to be something like 2, I think. I'll have to test this by hand later. Then we're going to do we're going to recursively call tox on b, c, a plus b plus c, and then we have to do n minus 1, something like that. Otherwise, if t is less than n, we return c. I think it's something like this. This is going to be wrong because I really need to test this out. But it's going to be, let's check it. 149. So we're off by 1. So maybe this one should have been 001. 001. Let's see. 81. Oh, because I have 3 and then already in there. 44. Yeah, there you go. There's a more scientific way of doing this, but on a test, and I'm treating this as if I'm on an actual test, I don't have time to. Right now, I'm even blanking on the theory of which numbers go here and here. I just know that this is the general structure. And this is close enough, really, I just have to change a little bit of this. So that's why I'm just putting this in, and I'm just going to fib around the structure until I get it correctly. So, yeah. And I got it. So let's check this. Yep, that works. And let's check this. Yep, that works. And then finally T100. Yep, that works. Okay, there we go. That's the solution. It's about the same as Fibonacci. You just have to know that, okay, you need to have some extra doodads going on. I'm strong. Oh wait, let me climb this up. m digit Armstrong number is a number which is equal to sum of the digits mth powers, where m is how many digits, I think it was. Yeah. So first we need to figure out how many digits are in the Armstrong number, and then we have to multiply each of them. Now fortunately we have something called where is it? Where is it? Int list. Yeah. Int list would convert this thing into a list, which is kind of cool. We can use it. So we're gonna say Armstrong. So since I already made int list, so x. So where? So I'm gonna do a bunch of calculations down here. Where list is equal to int list x. So this is the x as a list. Len is equal to the length of list. So now we get how many digits are in it. So this should actually be the digits. I'll just call it digits. I'll call it m. I'll call it m to match this. Okay, so m is the length of the list. This is actually the list. So what are we gonna do? We're gonna take every element from the list. So we're gonna say n, every element from the list, and we're gonna do n to the power of m. We're gonna do sum on this, and then we're gonna do x is equal to the sum of this. So if x is equal to, so we take each element from the list, which is this turned to the list, raised to its own power, Okay, that should work. Oh shoot! No. This doesn't quite do it because wait, we need the first n. Okay, so this just generates an Armstrong number. Oh no, this just checks if a number is Armstrong. Oh my god. Arm is Armstrong. Is arm int boo is arm x is equal to this. Yeah, we'll do that. Okay, cool. So Armstrong of x actually has to do something else. We have to what? Okay, yeah. So we have a filter for that. So we'll say, we'll say, given n, which is from 1 to infinity, if it is an Armstrong number, we'll keep it, and we'll take x of them. This should hopefully work, I think. I haven't tested this yet, but we'll see. Yeah. Oh wow, those are our Armstrong numbers? Holy shit. Okay then. Let's see. Oh, okay, yeah, cool. Let's see. Seriously? It's gonna take a little while. No, that works. Okay, cool. Let's see. So we're trying to look for this last thing. Ah, it works. Okay, cool. Only took 0.79 seconds, which is actually pretty slow. Okay, so that's that. This is the first. Are those the first 10 questions? First 11 questions. I managed it in under an hour, so it is manageable. Now that's it. I do admit, of course, I have far better practice of this than you guys do. So yes, of course, I'm going faster than you guys would. But I'm trying to. But I am doing this as if it was a test. So I am thinking through it and trying to explain it, guys. Explain it out to you, and like do it like on a test. Now you might, of course, be a little slower than me, but it's able. You can get 10 of them correct within the time span of the 2 hours. So it is possible, and they're not actually that awful difficult. Some of them I messed up a little bit, so I didn't need the square root test here. I can just actually delete that. I'll delete it just to not mess you guys up. But like some of them take a little more than one line. Although you could probably do them in one line, but right now I'm just going for speed rather than nice coded functions. But it's possible. It takes practice, so yes, you have to practice. Lots of practice. Yeah. What's this? Define. What are we doing here? Whoa. Okay. Test vectors for my convenience. Why, thank you. Why, thank you. But I don't. Okay, so we can use this later. We have to define the. Yeah. We have to define vector type 3. Okay. Right now, vector 3 is equal. It's a record which has an x0. Let's take a type A. X0 is of type A. x1 is of type A, x2 is of type A, I think. Is that what we're looking for? Yep, okay. Define instances for a couple of things. Instance plus on vector 3A. Actually, you know, I'm going to copy paste. Equal or 0 minus plus. Okay, cool. Where plus, given that we have plus on A, where plus x, y, so these are two vectors, we're going to say we need to make a new vector where x0 is equal to x dot x0 plus y dot y0. Yes, x1 is equal to this should be x0. One, 2, 2. There you go. Okay, x0, x1, x2. Cool. Should really test these, but I'm not going to. Instance minus copy, paste, minus, 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 minus. Let's paste it again because we need what? Equals, or, and 0. Oh my god. So given that it's equal, equals. Oh my god. Wait. This is gonna have to be quite a bit different. And so we're not storing anything here. And no. Equals. Actually, I'm not gonna do this. I'm just gonna load this into a list. Oh my god, so many stuff. No, that stays. So x0 equals to x0, y equals y0, None of this guy here. And they all need to be true. And okay. Okay, so let's actually, we do need to test these though, but let's start equals A plus B. Four. Yes. A minus B. -2, 0, -2. Yep. Equals B equals A less than, okay, yeah. Equals B, which should be false. Yep. A. Yep. Okay, cool. Cool. Okay. And then we need ORed. So something like, it's going to be almost the same as ORed, given that it's less than, yeah, so less than alright, we need to ORed based on distance from origin. So for this one it was what? Shit. Okay. I'm gonna do a where. Subwhere. Okay, so subwhere. D of x is equal to x dot x0 squared plus x dot x1 This should be 2, this should be 1, and then dy is equal to, all of these need to be y. So dx less than dy. Let's start is equal to a less than b. Whoa! Whoa, 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 whoa. Oh, it's because of this. Right. Blah. Okay. The reason why is because I'm restricting this to specifically an integer. Because when the reason why this happens, so I'm just trying to figure out why is this happening, is because this is a specifically integer, meaning that this hat becomes restricted to an integer. So in order to guarantee that we're not doing that, we're gonna have to, well, we're gonna code this for the more general of the two, which is the real, and just convert them to reals. This should work, hopefully, I think. Overloading to real could not be solved. To real. There we go. Okay, cool. So there we go. Those are the 3 instances. The last one is, yes, the hardest, but it is what it is. Let me see. Define the record type, record instances. Yeah, that's all. That was this thing. Cool. Using your defined record, if they are linearly independent, they're linearly independent if multiplying every component of one vector with a factor will give you the other vector, because they have okay, so linear independence if multiplying every component here by a factor. So the trick to this isn't multiplication, but rather division, because we can't generate a list of integers and multiply them, but we can do something like GCD. So, well, we can't do GCD because reals won't work for GCD. So we have to do division or something like that. So we have to do, I don't know. Well, they all have to divide by the same stuff. So x and y. So we have to do, I don't know, x dot x0 divided by, so something like x dot x0 divided by y dot x0 is equal to, oh my god, this is going to be a little painful. Where? Okay, a is equal to x dot x0 divided by y dot y0. So this is the multiplier between those two. X dot x1 divided by y dot y1. C equals x dot x2 divided by y dot y2. Oh, this works on real. We already know all this. Cool. Equals a equals b, and b equals c. That should work, hopefully. Let's test the start equals linear dependent. x0 equals 1.0. X. Do I have these written out already? 4, 5, 6. 1, 2, 3, 4, 5, 6. Which is what? Do I have these written out? Please tell me I do already. 1, 2, 3, 4, 5, 6. Yeah. C and E and C and D. Okay. C and E. Okay, so, oh, yes, because it's x, and I just make that mistake. False. True. Alright, cool. Works. Moving on. Okay, so, one of these. Right. These are the Pedro problems. Oh, yeah, I remember these. These are the Pedro problems. I didn't like them. Anyways, one of the most important operations in ray tracing is calculating the determinant. Calculate determinant for two 3D vectors by doing a whole load of crap. Okay. Yep. Okay. So we're gonna say there's an A and a B. Yeah, we're gonna say there's an A and B where, copy this crap. You're gonna be called something else. T U V equal to x0 equals t, x1 equals u, x2 equals v. I think this should work. I'm not gonna check that, but let's see. Okay. 1 2 1 3 2 3. 1 2 1 3 2 3, and there's a F. 5 10 5. Okay, so we could do determinant. Oh my god! Determinant 3D vector. Start equals. Was A and B? I think it was. I don't even remember what these guys called anymore. We should get a 4 negative 04. We flip them. We should get the opposite. Yep, and if we get, and I think it was A and F. It was. There we go. Yep. Okay. Cool. Okay, so that works. I just copy pasted his thing. At least he was nice enough with that. Yeah. Okay. And 15. Oh, I really do not want to do 15. Oh my, what the hell? Partition the problem into 3 smaller 2 by 8 matrices, 1 for each color. And what in Pedro? Why did you do this? Print Hungarian flag. I'm tempted to say, well, since we're printing a very specific Hungarian flag, that, to be completely honest with you all, but I know that's not what we, wait. Really? We just need 2 posts? I mean, what's the... Okay, so he wants you guys to do a list comprehension on this. I'm too lazy to do this one. I'll be honest with you guys. I'm too lazy to do this because you have to do a 6 by 8 matrix flag and some shit. Nah, it's fine. I mean, if you already printed out the values, just there. You don't need. Okay. Anyways, that last question was a little painful. It's not my style. Anyways, so this is the midterm all done. It took me an hour and 15 minutes. I was definitely rushing through all of these. Some of them can be solved better or with smaller solutions, but I'm showing you what I come up with if I just run through it off the top of my head and just kind of do things. And yeah, I mean, see, most of them aren't awfully difficult. There's stuff you've done before. I know some of you have written some much longer solutions, but a lot of times you don't need something really long, like this one. This is the one I wrote. And I remember that because the other one I wrote didn't make it into this test. But anyways, this is the one I wrote. Yeah, it's lazy. I always write lazy things, but like here you can see, like for example here, our life was made significantly easier by just doing instances, because then we can subtract. You know, we can do subtraction just with subtraction. We can use sum. We can use a bunch of things. So take away from this test, and while the second test will involve only materials from the second half, don't discount the stuff from the first test, because really you can still use list comprehension and instances to your advantage. So like here, this is probably one of the biggest takeaways. This problem, which is actually kind of a little messy and can be a little difficult, I just use instances. Yeah. I hope this helps, and I'm going to end this video now so that I can record sample and term solutions. Ta-da!